All right, so we fitted the logistic to single variable birth weight. Now, logistic regression works just like linear regression. We can do simple linear regression with a single variable. We can do it with multiple variables. And that's what we're going to look at right now. So, but it's exactly the same as we had before, with the same problems when you introduce. Which one should you introduce of all the candidates of covariates you've got there? Which one will do the best job of explaining? Then, do you have enough of them, etc.? The same. We're faced with the same problems, and we've got the same sorts of solutions. So here we are. So if we look at birth weight, if we relate it to gestational age, first of all, you can see the cutoff. We had cutoff here that we only had babies less than 1750. And if you look at the gestational age, then you can definitely see a relationship. This should not be surprising to anybody that we have a relationship between birth weight and gestational age. Okay, so instead of birth weight, maybe we should put gestational age. So here it is. Once again, just for explanatory purposes, broke up the gestational age into 3 groups. And we can see that what proportion in the less than 29 weeks, what proportion had BPD? We see that 70%. What proportion had BPD in this 29 to 30 weeks age group? It's down to 36%. And in this age group, it's down to like 10%. Remember with this that we said the baby had to survive at least 1 month in order to be a candidate to determine whether they had BPD or not. So just remember that this isn't for all babies born less than 1750. This is for those who survived 1 month. Mortality at this age is sizable. The proportion with BPD also goes down with gestational age. So the question is, of course, with multiple regression, same with multiple logistic regression, the question is not whether it goes down, but whether it's worth introducing into the argument. Is there variability with both? Because these two are very related. Are they collinear? Well, let's take a look, see. Here's a 3x3 table. Once again, this is just for expository purposes. Here's a 3x3 table, and what I've done is broken them up into those 3 groups, birth weight, and broken them up into these 3 groups, gestational age. Within each cell, we can take a look, see what proportion have BPD. So here is so this is about 80%. This goes down to 71% and then plummets down to 16%. Sure, the number is very small in here, so maybe we shouldn't get all excited about this, but it certainly looks like, even though within that birth weight class, that gestational age still has some impact in terms of determining who's going to get BPD or not. If we look at this class, we do see, once again, we see a decline in the number with BPD. So gestational age could still, in this birth weight class, could still have something to say. When we look at this last one, well, the first thing we notice is that there's a 0 here. Well, that's because not too many, in fact, 0 in this group of less than 29 weeks gestational age had birth weight in the 1.35 kilogram or higher. But anyway, with these two, we can still see a gestational age dependency in terms of the proportion who get BPD. And let me erase all that. Now, if we just constrain ourselves to the less than 29 weekers, we see that birth weight does impact the proportion with BPD. If we constrain ourselves to the 29 to 30, it looks like this is a little bit this is in the wrong direction, but both are less than what happened in the less than 950 gram category. And if we look at this one, then we see our monotonic trend that so birth weight still, within that gestational age category, birth weight still is informative. So this is arguing, first of all, that gestational age and birth weight are not totally collinear. If they were totally collinear, we would only see something along a diagonal like this. So they're not. Number one. Number two, the gestational age still has maybe some further information to bear on this issue of BPD over and above the information that birth weight carries. So here is a perfect argument for bringing both covariates in. So let's see what the theory tells us. So here's the logit for birth weight and gestational age. And so here is the birth weight coefficient. First of all, it's negative. So just like before, it's negative. So it's telling us that as the birth weight increases, the chances of BPD go down. Great. Gestational age is also negative. So once again, it's in the direction we might have suspected, that as the baby's gestational age increases, the probability of getting BPD goes down. Okay, so that's terrific. The p-values tell us that both those variables have a p-value less than 0.05, and so we would reject the null hypothesis that beta equals 0 for either of those. So that's okay, and this is confirmed, of course, by the confidence intervals. None of those confidence intervals include the value 0. We could have done it with the logistic command, and we see that now instead of 0, 1 is our odds ratio of 1, and we see none of those confidence intervals has a 1 in it, and so these are all important. Also, these odds ratios are all less than 1. So that means that they're protective. Same thing as before. So either a negative beta or an odds ratio less than 1 tells you that it's protective. So birth weight is protective, gestational age is protective. How about the fit? Here's the fit. So the red are the observed. We've seen those before. Within each cell, 80% in that cell had BPD. If we do the fitted value, is 0.766. There's observed, fitted, observed, fitted, observed, fitted, observed, fitted, observed, fitted. Not bad. Well, we couldn't have been better in the bottom right-hand corner than 0.085, but it doesn't matter. We're getting better and better in our fit by bringing in this extra covariate, namely gestational age. So it does help us there.